In this video, we're going to look at a specific type of differential equation that leads to exponential models. So one of the most common growth models is exponential growth and decay. So population is probably the most common one. You have this like small population, and then as it grows faster, and more people, it gets bigger. So you can grow or decay, but it's all dependent on the size of the population. So when the population is really small, this is like our output, the population is very small. There can only be a small growth. So if 1,000 people, we're not going to expect there to be 1,000,000 people the next day. There might be 1,002 people. But when the population is big, like 1,000,000 people, there might be 10,000 more people the next survey. So the bigger the population, the more it's going to change. All right, so the change is dependent on how much population we have. And we're going to see in a second that this will lead to an exponential model. All right, so let's solve this differential equation. All right, so dy dt equals ky. So again, any differential equation we had to solve in calculus is separable, which means we want to get the y's on one side and the t's in this case on the other side. So we're going to divide both sides by y and multiply by t. All right, so one thing that might be a little confusing is that there's this k and a t on the right, but k is just a constant. You can think about it as a 2 or a 3. So we can keep it on the side with the t, and now we can do our antiderivatives. The antiderivative of 1 over y is the natural log of y. Again, k is just constant. If you pretend this was a 2 and you took the antiderivative of 2, you would get 2 times the variable plus c. All right, so this k is going to stay because it's just a constant, and then we add in the variable t. And now we want to solve for y. So to get rid of this natural log, we use the exponential because they're opposites and they're going to cancel. And e to the kt plus c. All right, so this here is technically the right answer, but it's not the way you're going to see it because we do this a lot with these exponential answers. We can rewrite it like this first. Because if you're adding exponents, it's the same as multiplying. And then c is just a constant, it's just a number. E raised to a number is still just a number. So this whole thing we could represent as a different constant. All right, we'll use capital C. And then we still have e to the kt. All right, so this is the way you'll see it. This capital C, e to the kt, is the solution to this differential equation. So every single time we just have kind of one of these simple differential equations, just a constant times our output variable. It's always going to look like this as the answer. All right, what happens if we have an initial condition? So in this initial condition, we plug in 0 for t, and we get out a for y. All right, well, we know right away the general solution. The general solution is this. But we know when we plug in 0 for t, we get a for y. K times 0 is 0. And e to the 0 is 1. And we get a is c. So it's going to turn out that whatever this c value is going to be the same as whatever the initial condition for y is. So whatever this number ends up being, we just plug into the formula. All right, so this is the just summary of that, is that we have this kind of basic differential equation where it's just k times our variable. Its solution is always going to be this exponential model. All right, so it means we can do problems like this really quickly because we don't have to go through the whole process of anti-differentiating, integrating. I see this. I know the solution is going to be y equals c e to the kt because it's just 8 times our variable. The number here, that's our k value, so I can put an 8 there. And the number here, the c constant that we're looking for, is the initial value for our y. So just like that, we're done. We don't have to do any integration or moving things around. We know because this is the basic form, k goes there, initial condition goes there. All right, now we're just going to look at a couple AP style questions that use this idea. So again, you can pause the video and read through this. The main idea is we have this situation where we get this type of differential equation. The only difference is instead of y, we have a, but everything else is the same. All right, so which of these could be a solution? Well, we know the solution to this is going to be a equals c e to the kt. And c is the starting value, which we started with 400. So it would have to be 400 e to the kt. All right, so which of these looks like that? Well, this one's not an exponential. This one's not an exponential. This one is an exponential, but it has this like 399 over here instead of the 400 at the front. And this one looks exactly like our proposed solution. The only difference is they figured out what the k value was. All right, so this is our right answer. All right, and again, pause the video and read through it. But for this one, we have a change in population is proportional to the population at change. So the change in population at time is proportional to some k to the population. And this looks exactly like the things we've tried to solve. There's a y here and a y here. Same thing. We know the solution to this is p equals c e to the k t. At time t equals 0, the population is 300. So the initial condition is c. P equals 300 e to the kt. Then at time 24, the population is 1,000. So the population is 1,000. When I plug in 24, k times 24. So if you look at this thing, that's a 2, 24. If you look at this, the only thing I don't know in this equation is k. You might say you also don't know e, but remember e is just a number, 2.7, and so you know what e is. The only thing we don't know is k, so we can actually solve for k. So how can we do that? We can divide both sides by 300. And we've said this a lot throughout this unit, is that exponentials and logs are opposite, so I can take the natural log of both sides of this. And I can divide, oops, there shouldn't be the e anymore. It's just 24k. Because the natural log and the e cancel out. And I can divide by 24 to get the value of k. So now we know our general solution. We know now exactly what k is, and now we can finally answer the question, at what time t is the population 500? So now we want to know when the population is 500, e to the k t. So now we want to solve for t. We know what k is, but I'm just not going to write this big complicated thing. We'll put that in like the final answer. All right, but you could put the thing there. I'm just going to leave it there. But we solved this in the exact same way. Divide by 300. That simplifies. Take natural logs. And these cancel out, so I just get kt, divide by k. So the time we're looking for is this, and you can see that's exactly d. When I put k back in with the thing that we figured out, it was. All right, so this problem is a little crazy, but the starting step is exactly what we just did. Being able to solve an equation for something in an exponential is something you should be able to do with your logs. And then basically do the exact same steps for this one. All right, so you're just doing the steps using the information that's given to you in the scenario. All right, so a lot of new information. We have this basic differential equation. It always gives us an exponential model. You can always do what we did in the very first example of solving this using separation variables. That takes time, and also like in that first multiple choice question, you don't have all the information. The second one, they don't even give you the differential equation, so it might not be as obvious. So knowing this relationship is going to help you see those relationships when they come up on the exam.